In this video, we will explain about how to design a logic circuit and then how to combine this logic circuit with our arithmetic unit to form a combined arithmetic and a logic unit. First, we can consider the design of a logic circuit. Logic micro operations manipulate the bits of the operand separately and treat each bit as a binary variable. All logic operations can be obtained by means of AND, OR and NOT operations. It may be more convenient to employ a logic circuit with just these three operations. So we need two select variables, and by using these two select variables we can have 2 to the power 2. 4 operations can be selected. So we can include XOR function also to our circuit. So this is the simplest design for logic circuit. We have a 4x1 mux that will have 4 input lines, then 2 select lines. The output of the mux will be based on the select line values. So this AI and BI are single bits from A register and BI. This corresponds to ith bit from A register and this corresponds to ith bit from B register. So the circuit is for a one bit from or one stage. This corresponds to one stage. Then this based on these values of the this OR gate is connected with a 0 input, then XOR with a 1, AND with 2 and a inverter with 3. This this output will be AND of this A and B. This will be A XOR B. This will be A and B, and this is the complement of A. All these outputs will be available at these inputs. Then based on these inputs at the select lines, any one of the function or any one of the value will be available at a Fi. So that is here 0 0. OR operation will be selected. Then 0 1 XOR will be available as output. 1 0 AND operation will be available. 1 1 NOT or complement. Okay. And this one shows one typical stage designated by subscript I. We can repeat n times for an n bit. The same configuration can be repeated for n times for an n bit logic circuit. So next is how to combine this logic circuit with our previously designed arithmetic circuit. Assume that this corresponds to one stage of arithmetic circuit. It's one pair of bits. And this is corresponds to one stage of logic circuit. And this AI and BI, the bits are connected with this arithmetic circuit. The same AI and BI, they are connected with one stage of logic circuit also. Then the select lines S0 and S1, they are connected to this arithmetic circuit and also to the logic circuit. So based on the S0 and S1 values, that is select lines, any this that will perform this arithmetic circuit will perform some arithmetic operation, and that output will be available here, and the logic circuit will perform the corresponding logic operation. So both calculation will be done, that is arithmetic operation and a logic operation will be performed based on the value of S0 and S1. But based on the S2 value, any one of them will be selected as output, either logic or arithmetic. If the S2 value is a 1, then the output of the logic stage or logic circuit will be available here, and if S2 is equal to 0, then output of the arithmetic circuit will be available through Fi. So anyhow both arithmetic and logic operations will be performed and output will be available here, but only any one of them will be selected based on the S2 bit. Okay. But this is not the best way to design the ALU. So we have to consider some other strategy. So design of arithmetic logic circuit in more efficient way. So another method is we can consider this problem as a combinational logic problem. ALU can be broken into identical stages connected in cascade through the carries. Can design one stage of ALU and then duplicate it for number of stages required. So we have 6 inputs to each stage: AI, BI, CI, S2, S1 and S0. 2 outputs in each stage: FI and carry out CI plus 1. We can formulate a truth table with 64 entries and simplify the 2 output function. But this process is also more complicated or complex process. So we can consider another approach. Here we choose to employ an alternate procedure. Uses the availability of a parallel adder. We assume that we have already a parallel adder, and we can use that parallel adder to design our arithmetic logic unit. The steps involved are: first step is design the arithmetic section independent of the logic section. Second step, determine the logic operations obtained from the arithmetic circuit in step 1, assuming that the input carries to all stages are 0. Third one, modify the arithmetic circuit to obtain the required logic operations. So solution to the first design step. That is, design an arithmetic section independent of the logic section. That we have already done in our design of the arithmetic circuit in the previous classes. We have discussed that. So based on the select lines S1, S0, we can assume that this is our full adder circuit in the parallel adder. We have Xi input and Yi input. We will give AI always here to Xi input, and Yi for Yi input we can have this table. That is, when S1 and S0 is equal to 0, 0, then Yi will be given 0. 1, 0, 1 we have to give Bi, 1, 0 we have to give Bi complement, and when S1 and S0 is equal to 1 we have to give a 1 at the Y input. So we will have an expression like this: Yi is equal to Bi into S0 plus Bi complement into S1. Then we will get a circuit like this. So the connection will be like this. This is the arithmetic section independent of the logic section. Then for 4 bits, if we are considering 4 bits, then the circuit will become like this. 4-bit arithmetic circuit will be like this, and based on this S0, S1 and Cin values, we can have a different arithmetic operation that we have already discussed. So the x inputs, x1, x2, x3, x4, they are a1, a2, a3, a4. A directly given, a is directly given here, and to y inputs, the b bits are given, but through some circuits, some modification. Okay. Then this is the function table. When 0, 0, 0, y is equal to 0 and f is equal to a, that is transfer a. 0, 0, 1, f is equal to a plus 1 or increment a. 0, 1, 0, add b to a. 0, 1, 1, addition with carry. 1, 0, 0, add 1's complement of b to a. 1, 0, 1, subtract b from a. 1, 1, 0, f is equal to a minus 1 or decrement a. 1, 1, 1, all 1. Okay, then f is equal to a, that is again transfer a. This is about the function table for our previously designed arithmetic circuit. And we can just consider our full adder. So this is our full adder. Xi, Yi are 2 input bits. Then Cin is the input carry and Cout is the output carry. Fi is the output. So what is the expression for Fi? The expression for Fi is Xi XOR Yi XOR Cin. That we have already studied in previous classes for in the class for full adder. Okay. So Xi XOR Yi XOR Cin, that is the expression for Fi. Then if Cin is equal to carry, Cin is equal to 0, then what will be the value of Fi? Fi will become Xi XOR Yi, because for any a XOR 0 is equal to a itself. So Xi XOR Yi XOR 0, this will become like that. Then this will become Xi XOR Yi. So by inhibiting the input carry to the full adder circuit, we can generate the XOR operation. And solution to the second design step. Determine the logic operations obtained from the arithmetic circuit in step 1, assuming that the input carries to all stages are 0. So these are our S2, S1, S0. We have made here all ones, then 0, 0, 0, 1, 1, 0, 1, 1. Then xi inputs are we already set as ai's, directly given. Yi inputs are 0, bi complement 1 based on this S0, S1 values. Okay. Then the output fi will be, okay, ci is set as 0. That we already said that we are assuming that carries to all stages are made as 0. Okay, we are inhibiting the carry. So what will be the fi? Fi will be xi xor yi, that we have discussed just in the just previous slide. Okay, so this will become ai, and this will become ai xor bi, or XOR operation. This will become ai xnor bi. This is equivalence or xnor operation. Then this will become ai complement or NOT operation. So in this XOR and NOT is readily available, but here we have a transfer A and equivalence A that is not required as logic operation. So we can convert this transfer A and equivalence A into our logic operations. That is, we can we have to modify the circuit so that here we will get OR operation, and here we need AND operation. Instead of equivalence we need a AND operation. Modify the arithmetic circuit to obtain the required logic operation. That is our case. That is, here we have to modify in such a way that we will get a OR operation here and here and AND operation. That is, when 1 1 0 we need AND operation, when 1 0 0 we need OR operation. XOR and not already there. Okay. Then we have to consider how to modify to get our OR operation. So when S2, S1, S0, they are 1 0 0. Okay. Each stage generates the function. That is, we have to modify here. When S2, S1, S0 is equal to 1 0 0. In that case, we have transfer A. We have to modify that into OR operation. So okay. So when S2, S1, S0 is equal to 1 0 0, each stage generate the function fi is equal to ai. Okay. To change the output to an OR operation, what we can do is change the xi input to each full adder circuit from ai to ai or bi when S2, S1, S0 is equal to 1 0 0. In the previous circuit we will give ai to xi, but here the modification is, instead of giving ai we have to give ai or bi for the xi input. Okay. Then the output, our output function is actually xi xor yi xor ci. Then instead of xi, for xi we have give ai or bi as the input to xi, and yi will become 0. Why? Because here S0, S1 and S0 values are 0 0. For 0 0, what will be the yi? 0. That we are already designed. So this part is 0. Then ci we already inhibited, so 0. Then output will be ai or bi will be the case when the select lines are 1 0 0. Okay. Then next we have to modify to obtain AND operation. When S2, S1, S0 is equal to 1 1 0. So in normal case, or in our previous arithmetic circuit, each stage will generate the function like this: fi is equal to ai xnor bi. So we have to modify this to get ai and bi. To change the output to an AND operation, change the Xi input to each full adder circuit from AI to AI or B complement when S2 S1 S0 is equal to 1 1 0. Then the output will become Fi is equal to Xi XOR Yi XOR 0. This 0 is carry we made inhibited, so Xi XOR Yi. Then for Xi we will give Ai or Bi complement, and for Yi we will give Bi complement. Why? Here 1 0, S1 S0 value is 1 0, then 1 1 0 we have to give Bi complement that we have already designed. Okay, so Bi complement will be here. Then we will get an expression like this. Here Bi complement Bi, this will be cancelled. Here also Bi into Bi complement, this will also be cancelled. So we will get Ai Ba. That is the AND operation. Now we have modified our circuit to obtain OR and AND operation.